Well, hello, ladies and gentlemen. Your daily dose of Dorfler here, coming at you live or not live from my classroom. Sorry about that. All right. So, we're here for part two of section two, I believe. Yes, part two of section two, where today's video is going to be a little shorter than yesterday's video. But section three's video, it's going to come out tomorrow. I'm going to tell you now, it's going to be a little longer than normal. Okay. So you might need to, if you want to split it up into a couple days or just speed up the video playback, up to you. But how it's kind of working out, section three, there's a lot of information. I'm going to try to speed up and address only necessary bits that I think we could probably focus on, and then other things we could probably just kind of push off to the side. But like I said, it might be a little longer, just giving you a fair heads up. Anyway, so far in section two, we've talked about metathesis reactions. Again, the do-si-do reaction, to where we have the ions of the reactants. When they react in the solution, they essentially dissociate. There's that word that we talked about that you need to know. So that means they break apart and they switch partners. So we saw in a molecular equation yesterday, which is basically an equation that is balanced. It shows you everything that's taken part, or shows you everything that's involved. Okay, we got the reactants, we got the products. There's that. So you see here we have silver nitrate reacting with potassium chloride, and then we do-si-do, we switch around, we exchange partners, and silver now goes and joins with chlorine, and potassium goes and joins with nitrate. Okay, but what we're focusing on today is we're going to be looking at and creating what is called a net ionic equation, okay? What that means is we're taking these metathesis reactions and we are going to basically dissociate what can be dissociated, okay? And then we are going to eliminate certain ions that are essentially non-players, okay? They don't really have a huge role in what is happening in the overall reaction. In these types of reactions, we're looking at reactions that have precipitates, things that are insoluble, okay, like silver chloride, okay? I'm going to give you a big hint right now. Liquids, and when I say liquids, it's not aqueous. Liquids is like water, okay? Solids, most importantly right now, solids cannot dissociate. Okay, that's why they're solid. Okay, they're not soluble. So when we go and do this in a precipitate reaction, in a metathesis reaction, solids do not dissociate. So that's going to be a big hint into what we're getting ready to go look at. Anyway, we're going to take this equation right here that we see right now on our screen, and we're going to use it to create our net ionic equation. Okay, I'm going to go ahead. Okay, first, we go from molecular, it's kind of a two-step, a three-step, however you want to call it, process. Okay, we start off with the balanced molecular equation, and then we go into the ionic equation. In the ionic equation, all strong electrolytes, meaning strong acids, strong bases, soluble ionic salts, are going to be dissociated into their ions. Okay, going back to this first bullet point, we said that there are 7 strong acids. We listed them. There are 8 strong bases. We listed them. And soluble ionic salts, we can use solubility guidelines. That goes back to what I was just saying a few moments ago. Precipitates, or the solids that are formed after a reaction, are not soluble ionic salts, so they cannot be dissociated. Anyway, what an ionic equation does, it more accurately reflects the species that are found in the reaction mixture. So, again, we took this equation, this reaction, and we split up and dissociated anything that we could, okay? Silver nitrate is a strong electrolyte. It's a soluble ionic salt. So it gets split into silver and nitrate ions. And I'm going to show you in the practice example here that if there's a subscript or a coefficient, those do play a role. We'll get there a little bit later. None of these in here had a coefficient or a subscript. It's pretty straightforward. Potassium chloride. It's a soluble ionic salt, strong electrolyte, so it gets split up into potassium and chloride ions. Then it forms silver chloride. Not soluble. That's why you do not see it split up. Okay? And then potassium nitrate is soluble. It's a soluble ionic salt, therefore strong electrolyte, therefore can be dissociated. Okay, so that's the ionic equation. So again, you start off with the balanced molecular equation, go to your I keep wanting to say it. Start off with your molecular equation, go to your ionic equation. It's kind of like your middle step. And then you get into your net ionic equation. To form a net ionic equation, you cross out anything that does not change from the left side of the equation to the right side. So if we look here, the notes have already gone ahead and crossed out nitrate. Because look, nitrate's the same on both sides of the arrow. If it's the same, then it gets crossed off. Same with potassium. Potassium does not go away, does not change. It's K plus on the left and K plus on the right. So what we're left with, as you see here, we've got the silver and we've got the chloride ions on the left side that are not crossed off because they started off as aqueous in nature. They combine to form a solid. So they have changed. So they are the active players in this reaction. The only things that are left are those things that are changed, okay? And so anything that we crossed off and removed from our net ionic equation, which I want to go back a minute, what you see here, right here, where my mousy mouse is, this is a net ionic equation. What you're left with, okay? What has not been crossed off and brushed away. This is a net ionic equation, okay? The things that we do cross off and get rid of are what are called spectator ions, okay? They just spectate the reaction taking place. They don't really change from what they started with, okay? That's a term you need to know. So here's how we do our net ionic equations. 4 steps. First, you have to write a balanced molecular equation. You will then dissociate all strong electrolytes. You'll then cross out anything that remains unchanged from the left side to the right side, and then you will rewrite the net ionic equation with only the species that remain. All right, let's look at a practice one here. Now, I'm going to say you're going to come across some situations that you are going to have to determine what the formulas are. It has been 2 chapters of me saying that you have to know how to do this. Okay, honors class has to know how to do formulas at this point. Anyway, we are up here. Write a net ionic equation for the precipitation reaction that occurs when aqueous solutions of calcium chloride and sodium carbonate are mixed. Okay, so first thing is we have to figure out what our formulas are going to be for our reactants. Then we have to figure out what our new formulas are going to be after we do and switch them around for our products. And then we've got to balance it. So our first one was calcium chloride. Calcium is 2+, chloride ions are -1. You whoop them and you get CaCl2. It's aqueous because we're told it's aqueous. Our second reactant is sodium carbonate. Sodium is a +1. Carbonate is a -2. You whoop them and you get Na2CO3, again aqueous. Yeah, I know that arrow is not in the right location. There's some formatting issues between my computer here at work and my Chromebook at home. So just know that arrow is supposed to be a little higher up there. Anyway, we've got our reactants now. And now we have to do them. We have to exchange partners. So calcium is going to go with carbonate and sodium is going to go with chloride. Okay, so we get CaCO3 and NaCl. Okay, well, NaCl is sodium chloride. It is a soluble ionic salt. So, it's going to remain aqueous. Calcium carbonate, again, if you look at the solubility guidelines that we talked about yesterday, you will see that it is, in fact, a solid. So that is our precipitate. So now that we've identified our products and identified which is the precipitate, then we go ahead and balance it. And we see that we put a coefficient of 2 in front of the sodium chloride in our product. I mentioned not too long ago that subscripts like on the 2 on the chloride or on the sodium, or the coefficient of 2 in front of the Na and Cl are going to play a role when we do our ionic equation, where we dissociate everything that can be dissociated. So, next step, according to those 4 steps, is we need to dissociate all strong electrolytes. So, calcium chloride gets put into Ca2+ and 2 Cl-. Again, that 2 that's on the Cl right here from the molecular equation gets put in front of the Cl- ion in the ionic equation. And so same thing with the 2 on the sodium. Gets put up as a coefficient for its ion, and carbonate is also separated. It has a 2- charge. On the product side, again, calcium carbonate. It is a solid. It cannot dissociate, so it remains as CaCO3. And then sodium and chlorine has that. Sodium chloride has the coefficient of 2, so that coefficient of 2 gets applied to both the sodium and the chlorine on the product side. So what our last things is, or our second to last step is, we need to cross off all the spectator ions, things that do not change. So if you look at chlorine is 2 Cl- on the left and 2 Cl- on the right, so that would be crossed off. Sodium, 2 Na+ on the left, 2 Na+ on the right. That would be crossed off. Calcium and carbonate started off as aqueous and then combined to form a solid. So they are what changed. So to finalize your net ionic equation, you have Ca2+ aqueous plus CO3 2- aqueous yields CaCO3 solid. And that is your net ionic equation. So let's go down to the practice exercise here, okay, where we are to write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of silver nitrate and potassium phosphate are mixed. Oh, I did it again. Yep. So I'm going to have to pause this video and going to pause this video and come back to you and join videos because I'm having some technical issues. So hold on tight. All right, and we are back. Sorry about that. One program does not like to work with another program if I already have it open, so yada, yada, yada. I fixed it. All right. So back at this, we are to write a net ionic equation for the precipitation reaction that occurs when aqueous solutions of silver nitrate and potassium phosphate are mixed. Okay. So back to this. Okay, I have a new marker, so hopefully I can write a little clearer. So we have silver nitrate, and of course it doesn't work. Great. Okay, let's try this one. So silver nitrate. Okay. Silver nitrate. Aqueous. Okay. Plus, it was hold on one second. Okay. It was potassium phosphate. So many things not going my way right now. So potassium phosphate. Phosphate has a 3- charge. Okay. Potassium, 1+ charge. So we get the formula K3PO4. aqueous. Okay. Now, again, we're not going to balance it just yet. We got to predict our products. And so we're going to do-si-do. Potassium is going to go with nitrate. Silver is going to go with phosphate. And we're going to get KNO3. I'm going to leave a little space just so we can determine who is the precipitate. And again, silver is +1, phosphate is -3, so Ag3PO4. Okay. There we go. So now we've got to look at determining which one of our products is going to be the precipitate. Okay. Well, potassium nitrate we know is soluble with anything. So that means that just by going off what they're saying, that potassium nitrate is going to be our aqueous. But just to double check, let's go use our solubility guidelines. Phosphate, okay, is typically insoluble unless it's bonded with ammonium or alkali metals, which silver is not any of those. And so that means that this is our solid. So I'm not going to take a whole lot of time in balancing this. I'm just going to show you what we need to do to balance this. You need to put a 3 in front of the silver nitrate on the left and a 3 in front of the KNO3 on the right. It's balanced, okay? We balanced a ton of equations back in chapter 2, I believe, maybe even chapter 3. Sometimes they run together. So, you can do that. Anyway, next step is we have to dissociate what we can, okay? So again, for our ionic, so this is our molecular. I'm going to write that there. Next is going to be ionic. And this is going to take up some space here. So I'm going to try to do this as neatly as I can. So silver nitrate is going to break up into 3 Ag plus aqueous plus 3 NO3 minus aqueous. Okay, so far so good. Because again, we're putting that coefficient to both silver and nitrate. Plus 3 K plus, because that subscript on the K goes with it. And that's also aqueous. Plus PO4 3 minus aqueous. Okay, and I'm going to draw the arrow here because I'm going to run out of room. Okay, so onto the right side now. We said that potassium nitrate was soluble, so 3K plus aqueous plus 3NO3 minus aqueous plus silver phosphate is a solid, therefore it cannot dissociate. So Ag3PO4 solid. Okay, so now we have to go and, for our second to last step, identify what has not changed. If we go here and look at the silver, okay, silver is a positive ion in the aqueous form on the left, but it's now part of a solid on the right. So we can't cross that out. We have 3NO3 minus on the left, aqueous, 3NO3 minus aqueous on the right. So we can cross those out. Those have not changed. 3K plus aqueous on the left, 3K plus aqueous on the right. Did not change. And then phosphate, PO4 3 minus aqueous, then joins with silver to form a solid, so it does not get crossed over. So nitrate and potassium ions are the spectator ions. The last thing we need to do is write our net ionic equation. We just rewrite what is left. 3Ag plus aqueous plus PO4 3 minus aqueous yields Ag3PO4 solid. And this is your net ionic equation. Okay, if this stumped you, rewatch the video because I explained every step in pretty clear detail. Okay, again, you might have to watch this portion right here a second time. Okay, or go over the steps. Okay, it's somewhat quick, takes up some space, but again, it's not math involved. So that actually is going to wrap up section 2. Again, section 3 is going to be a little longer. It's going to give you a heads up now. So give yourself some time on that. And then I'm going to have some more things to say towards or at some point during the section 3 video. Anyway, have a good day, everybody. I'm going to have to splice these 2 videos together, and hopefully it works. Bye-bye now.